Hello, welcome to part 2 of the pre-algebra basics videos. Today we're going to work on addition and multiplication properties, in other words the properties of arithmetic. But before we do that, I want you to consider the following expression, which is just x plus y. Very simple expression. This is nothing more than the sum of two numbers, or two terms, right? So x and y are terms. They're trying to add together. However, remember that a term is actually a collection of factors. So we're going to define x as the product of a and b, which are factors of a and b. In other words, we're just showing that x is made of these two factors, a and b. And then we're also going to define y as the product of c and d. So these are the two factors that make up y. For example, if x was 12, then a could be 3 and b could be 4. So because 3 times 4 would be 12. So the term x would be made from the factors 3 and 4. They could be other values as long as their product would be 12, right? For example, a could be 2, b could be 6. Okay, so now we're going to use the substitution property to replace x with ab and replace y with cd. We can now see that x and y were just the products of some factors, and the sum of those products would have the same value as the sum of the original terms. So moving forward, it's important to remember that terms are groupings of factors. It's just that sometimes in the multiplication has happened before we actually showed up, before we got around to looking at the problem. Now we can finally start talking about the properties of arithmetic. So these properties are all about how arithmetic, which is the way in which we perform operations, both works and can work. So how it does work and in any specific situation, and also how it can work in other situations. You can pick one way or another way. It doesn't matter. So you'll notice before we start that I've actually separated this page into an addition and subtraction section and a multiplication division section. That's because while these properties share names and sort of underlying meanings, they apply differently for these two sets of operations. The first property we're going to talk about is one that's often misunderstood, and that is the associative property. So first off, the associative property states that in any statement with more than two terms, any two terms may be added without changing the result. Now, when I read the general form here, I want you to pay special attention to how I emphasize. Here we go. A plus b plus c equals a plus b plus c. The way that I'm emphasizing is designed to show that I'm trying to add a plus b and then add c. Or, on the right side, I have this term a and then I'm adding the sum b plus c to it. So we can see that the left and right sides are the same, right? If I add these three things together, of course I'm going to get the same result. It's the same three things. But what the associative property is really saying is that if I choose to add two terms together, it doesn't matter which two terms I actually choose. Here in this example, I'm going to add 3 and 4 on the left first, and 4 and 5 on the right first. 3 plus 4 is 7, and 4 plus 5 is 9. For the left side, 7 plus 5 is 12, and for the right side, 3 plus 9 is also 12. So we come to the same answer either way. So it implies that only terms that are next to each other can be added that way. But really, I could add any two terms I want. Had I decided to add 3 and 5 first, that would have been 8. And 8 plus 4 is also 12. For multiplication and division, in any term with more than 2 factors, any 2 factors may be multiplied without changing the result. Remember from earlier that a term is made of factors. And so when we say in any term, we're really saying that you can only do this within a term. You can't, for example, decide to multiply by a factor that's in a completely different term. So if I've got 4 times 5 plus 2 times 3, I can't suddenly multiply the 5 from the first term by the 3 in the second term. That would just produce utter chaos. So here's the general form. Pay attention again to the way that I emphasize my words when I'm reading the general form here. A times B times C equals A times B times C. The emphasis that I'm putting on the words is sort of like showing you where the parentheses go. When I say A times B times C, that little pause tells you that the first 2 things I said should be in parentheses. Likewise, when I say A times B times C, the little pause followed by the more quickly read portion of that, like A times B times C, here I'll read that a little faster, shows that the B and the C should be in parentheses as well. So here's an example. I'm using the same numbers for A, B, and C, 3 times 4 times 5. Okay, so on the left side I've got 3 times 4 first, which is 12. And on the right side I've got 4 times 5 first, which is 20. 12 times 5 is 60, and 3 times 20 is also 60. And just like last time, even though the general form implies that I can only multiply 2 factors that are next to each other, I can actually multiply the factors within a term in any order I want. Because if I did 3 times 5 first, that would be 15. And 15 times 4 is 60. So, same answer again. The next property is a commutative property. Now, a quick word about that word, commutative. It's got this root word, commute, which means to go back and forth. You might hear about someone's daily commute, which for adults might be to work and back, and for students might be to school and back. So like in the morning, you go to school. In the evening or afternoon, you come back. And this act of going back and forth, that's your commute. To commute is to go back and forth. The commutative property states that because terms can be added in any order, terms may be rearranged into any order. They may be moved around. That wording refers back to the associative property, where we said that we can in fact add terms in any order. So, if you can add terms in any order, then why would the order of these terms actually matter? So, yes, we can move terms around as desired. So here's the general form. A plus B is equal to B plus A. I can take the term B and I can swap it with the term A. Not a problem. Likewise with the multiplication version. Because factors within a term can be multiplied in any order, factors within a term may be rearranged into any order. So yet again, that goes back into the associative property, where we said that we can in fact multiply factors within a term in any order. And once again, I don't mean to harp on this point, but it is very important to remember factors are the things that make up a term. So we can only work with factors inside of a term. We can't suddenly move a factor out of one term and put it into another. So the general form just says that A times B is equal to B times A. I can swap the factors around. It still works fine. Okay, next property is the identity property. Identity property, this is a very easy one. In mathematics, an identity is one of two things. The first is it's a statement that's true no matter what. The other thing that an identity is is the method by which an operation can be performed without actually changing a value. So, if you think about what we can add or subtract without changing anything, that would be 0. Adding 0 does not change a value. It's a very straightforward property, and I'm just going to bet you can figure out what the identity property of multiplication is for yourself. Just think, what number can you multiply anything by without changing the value? Well, that would be 1, wouldn't it? And so here's our general form. So the identity property for addition is a plus 0 is a. And the identity property for multiplication is 1a, 1 times a, is also a. In other words, if I add 0, I end up with whatever I started with, and if I multiply by 1, I end up with whatever I started with. Next property is called the inverse property. The inverse property is all about what operation undoes or reverses or cancels another operation most directly. And so when we talk about the inverse property, we'll also be talking about what are called inverse operations. So for addition, the inverse operation is subtraction. It's the thing that undoes subtraction. So for any operation, there is another operation that will undo it. The inverse operation of addition is subtraction. If we have a value, and then we subtract the same value, we get 0. Or, if we have a value and add something to it, we can then subtract that same thing that we had added to it, and end up having effectively done nothing. If I, give you $1, and then I take it away from you, you have the same amount of money as you started with. Likewise, for the multiplication inverse property, for any operation, there's another operation that'll undo it. The inverse operation of multiplication is division. If I have a number, and then I divide it by itself, I will get 1. Also, if I have a number, and then I multiply it by something, and then I divide it by the same thing that I just multiplied it by, I'll get back to the original number. Now before we move on, we should note here that an inverse operation works both ways. Imagine that I add 3 and then subtract 3. I've effectively done nothing. But what if I subtract 3 first and then add 3? Same thing, right? I took 3 away, but then I put it right back. So I've effectively done nothing. Likewise with multiplication and division. If I divide by 3 first, and then I multiply by 3, that multiplication by 3 will still undo the division. And we'll see this idea pop up again later. Okay, finally, we're here at the distributive property, which is possibly the most difficult one to understand or remember. First, let's start with the word salad. The distributive property states that when multiplying two values with multiple terms, we multiply each term from the first value with each term of the second value, and then add all of the individual products. Okay, so that's a lot to take in at once. Let me explain with an example about what's going on here. So, in this example, we're just going to go ahead and figure out well ahead of time what answer we should get when we multiply 8 and 12, which is 96, yeah? Great, good, cool, also great. Now, let's make it needlessly complicated. 8 times 12, would you agree with me that if I split the factor 12 into two terms, 10 and 2, I could write it like this, 8 times 10 plus 2. Because 10 plus 2 is 12, so that still says 8 times 12. Cool. The sum of these two subterms is still 12, so by substitution, we're totally allowed to do this. Now we're going to use the distributive property to multiply these two subterms each by 8. So first we're going to multiply 8 and 10, and then we're going to multiply 8 and 2. And that's going to give us the product of 8 and 10, and the product of 8 and 2, and then we add together the products. So 8 times 10 plus 8 times 2. Okay, 8 times 10 is 80, 8 times 2 is 16, and 80 plus 16 is 96, which is exactly what we were supposed to get. So it works, but why? So, okay, we got to get into the language of multiplication here. 8 times 12 means that we have 8 sets of 12. So there's a group of 12, and then another group of 12, and then another group of 12. There's 8 of those in total, right? 12 is just the same thing as 10 and 2. Therefore, 8 times 12 would be the same as 8 times 10 plus 2, as we said earlier, which means 8 sets each of 10 and 2. I'm going to have 8 sets of 10 and 8 sets of 2. Now we're not going to dig all the way down on distributive property in this video. I'll be making another video on that later, as well as deeper dives on a couple of other topics we've covered, especially like commutative property. However, I'd like to cover another example before we move on. 13 times 27. Now, my calculator tells me that this is 351, but let's figure it out using the distributive property, shall we? So we're going to split 13 into 10 plus 3, and we're going to split 27 into 20 plus 7. So I'm just doing the tens and the units. Now, according to the distributive property, I have to multiply each term from the first value by each term of the second value. So what I'm going to do is I'm going to start it with that 10, and I'm going to multiply it by the 20, and then I'm going to multiply it by the 7. So that's going to give me 10 times 20, and then 10 times 7. Now I'm going to move on to the 3, and I'm going to do the same thing. 3 times 20, and 3 times 7. So here's all of those individual terms laid out. 10 times 20 is 200. 10 times 7 is 70. 3 times 20 is 60, and 3 times 7 is 21. And if we add all of those together, we're going to get 351. Cool. Since a factor can be split into as many terms as you'd like, the size of the factors can continue to get larger. But that'll be another video when we dive deeper into distributive property. Home stretch. It's now time for what I call the operative properties of equality, otherwise known as symmetric operations. These are also sometimes called the properties of algebra, since this is now getting into how we actually solve algebraic equations. Don't get intimidated though, these are actually some of the easier ones we'll see today. First up, we have the additive and subtractive symmetric operations. Adding an equal value to both sides of an equation does not invalidate the equality. All that means is if you add the same thing to both sides, the left side and the right side will still be equal to each other. It won't necessarily be the same number, but the values will be the same as each other. So, here's an example. We're going to start off with a very obviously true statement. 6 equals 6. That's by reflexive property. We're going to add 11 to both sides. 6 plus 11 equals 6 plus 11. And 6 plus 11 is 17, so we get 17 equals 17. Okay, so by reflexive property, still true, but, well, no duh, right? Of course, if I do that, then it's true. It's not the same number, but the two numbers on either side are still equal to each other, and that's all we care about. So, if that was too obvious, let's try an algebraic expression, or equation rather. This is x minus 3 equals 7. So we want to know what x is, and this equation is easy enough that we could guess it, but we want to know how we could do it with actual operations. So x is currently being reduced by 3. That's that minus 3 that's on there. And we want to undo subtraction by 3. Well, if we want to undo subtraction, we have to use the inverse operation of subtraction. Well, that would be addition, right? So I can add 3, and that will undo subtracting 3. But if I only add 3 to the left side, then the left side will be 3 bigger than the right side. So to make sure that it stays balanced, so to speak, I have to add 3 to the right side as well. So if I add 3 to both sides, the minus 3 and the plus 3 on the left side are going to undo each other, and that will leave me with just x, and then 7 plus 3 is 10. Oops. And then 7 plus 3 is 10. So here's another example. If I have x plus 4 equals 21, then I know that I have to subtract 4 from both sides in order to undo that addition of 4 onto the unknown thing, the x. So I subtract 4 from both sides, and then this plus 4 minus 4, they're going to undo each other and leave me with a 0. And x plus 0 is just x. That's the identity property of addition, remember. 21 minus 4 is 17, so we get left with x equals 17. Okay, so in general, if a is equal to x, that's just stating if we have something equal to something else, then I can add m to both sides, and m is just any value that I want. In the second problem, that was 3, and in the third problem, that was negative 4. You could also say that I subtracted 4 from both sides in the third problem, but subtraction is the same thing as adding a negative, and we'll talk about that at some point. So next up is the multiplicative symmetric operations. Just like addition and subtraction, we can freely multiply both sides of an equation by whatever we like and maintain equality between the two sides. So here we've got 3 equals 3. By reflexive property, we know that that's true. I'm going to multiply both sides by 4. 3 times 4 is 12, so I get 12 equals 12. Again, a different number, but the two numbers that are on either side of that equal sign are the same as each other, so it's a true statement. 12 is equal to 12. Now for the second example, it's important to remember that multiplication and division are inverse operations. So here on the left side here we've got a 21, and I'm going to multiply it by 3 and then divide it by 3. I'm going to do it in that order. 21 times 3 is 63. 63 divided by 3 is 21. So we can very clearly see that if you multiply by 3 and then divide by 3, you get the same thing you started with. So multiplication and division, as we've said before, are inverse operations. And because of that, we can do this the other way around. If I start with 21, and then I divide by 3, and then multiply by 3, well, 21 divided by 3 is 7, and 7 times 3 is 21, which puts me right back where I started. So it's important to remember that as we go forward. If I have the problem x divided by 7 equals 2, I can undo the division with multiplication. So I multiply both sides by 7. Division by 7 and multiplication by 7 will undo each other, and that will just leave me with x, and 2 times 7 is 14. In general, we will say that if a equals x, yet again it's just saying if the left side is equal to the right side, then a times m is equal to x times m. So I can multiply both sides by the same number, whatever it happens to be, and it will still be equal. One note that I want to make about this before we move on. We also know that anything times 0 is 0. In an algebra problem, imagine that we decided that we wanted to multiply both sides by 0. Well, we'd be left with 0 equals 0, which is a true statement, but doesn't tell me anything about the variable in an algebra problem. So in algebra, deciding to multiply both sides by 0 is not really a great idea. You don't want to do it. The last one, the division symmetric operation, shouldn't be surprising by now. We can divide both sides of an equation by any value. So up here we've got 14 equals 14. If I divide both sides by 2, then I get 7 equals 7, and it's still true. Up here I've got 3x equals 39. To undo the multiplication by 3, I'm going to divide both sides by 3. So if I multiply by 3 and then I divide by 3, I have effectively done nothing, and that will just leave me with that x. 39 divided by 3 is 13. So we can divide by whatever we like on both sides. Almost. Notice here that I've added this note that this is true only as long as the number we divide by, which I've called m, is not 0. Now we'll have another video about weirdness with 0 later, but for now just remember that dividing by 0 is the big no-no in math. You cannot do it. There are also operative properties for exponents, radicals, logarithms, and likewise there's essential properties of proportions and absolute values, but we're going to talk about those at another time. This video will be way too long if we get into that. We've actually skipped the 0 property of multiplication and division, but only because there will be an entirely other video about the 0. Just remember, 0 times anything is 0, 0 divided by anything is 0, and you cannot divide by 0. So that's, if you have 0 divided by 4, that's 0. If you have 4 divided by 0, you broke math. Oops. Okay, so here is the big ol' list of general forms for the properties of equality, the properties of inequality, and the properties of arithmetic that we've learned in this series. Thank you for listening, and I will have new videos out soon.